Hey guys, welcome to today's class. Have fun.
Okay, welcome to class today. So today we'll be looking at the topic latent heat. So the last two classes we talked about heat capacity, we talked about expansion. So we're trying to study the effect of heat energy on various states of matter. So today we'll be looking at latent heat. So we have three various phases or three various states of matter. You have solid, you have the liquid, and you have the gaseous states. Now, these states are they have a similar relationship to one another. Taking water as a typical example now we have the conversion of these states from solid. In case we have ice solid now, it's melted on application of heat energy to liquid and further application of heat energy to gases. Now, in the last class, when we talked about heat capacity, we are trying to tell us about the amount of heat energy that will be required to raise a unit mass of the substance by a certain degree Kelvin. So we are talking about the heat capacity, the heat required to raise the whole mass of the substance by 1 degree Kelvin, while the specific heat was the heat required to raise just 1 gram by 1 kg by 1 degree Kelvin. But in this case now, when we're talking about latent heat, we are concerned about the conversion from one state to another. Now, for a solid ice now on application of heat energy, you have the heat capacity in place already. The heat capacity in this case now is the amount of energy you need to increase the temperature of a unit mass per degree Kelvin. Now, in converting ice now into water, which is the liquid state now, the heat energy which you are going to be requiring to convert it from one state to another is what we refer to as the latent heat. Now, in the conversion of ice to water, you have an input amount of heat energy, you have its specific heat capacity, and you have its latent heat capacity. You have the mass of the object substance also. So latent heat is the quantity of heat required or needed to change the state of a substance at a constant temperature and pressure. So the quantity of heat required to change the state from this solid state to a liquid state under a certain amount of temperature and pressure is what referred to as the latent heat. So the latent heat is expressed mathematically as Q equals to mL, where L is the specific latent heat. So L is a specific latent heat, and Q, as always, is a form of energy is measured in joules. So our latent heat is measured in joule per kilogram, or can be joule per gram. So the latent heat is the heat we need or require to change it from one state to another. So latent heat depends on certain characteristics, certain factors. It depends on the material. Now you have ice. Now you want to convert into liquid. Now the amount of heat required depends on the material. First, the nature of the material we are dealing with. Depends on the mass concerned. Depends on the mass of the elements of the substance. It depends on the volume and the area of the material. It depends on the energy supplied. It depends on the state of the material. Okay, now we've said we want to convert ice into liquid. Now, a number of factors which are in place. One is the nature of the material. Now, the material, is it a metal? Is it a non-metal? Is it a wood? Is it So we have to know the nature of the material. Now, we are also going to be concerned about the mass of the material. How large is the material to determine the amount of heat. Also, you will be concerned about the energy supplied because the mass tells you the amount of energy you supply in order to convert it from one state to another. Also, we are also concerned with the volume and area. So the volume and area is also a factor to be considered. And we're also concerned about the states of the material. Is it in a liquid state? Is it in a solid state? Or is it in a gaseous state? So our specific latent heat L depends on these parameters which I've explained. Now we have specific latent heat of fusion. Specific latent heat of fusion. Now what do you mean by this? It says the quantity of heat required to change a unit mass of solid into a liquid at constant temperature and pressure is what we refer to as a specific latent heat of fusion. So the quantity of heat we require to change a unit mass of a solid into a liquid at constant temperature and pressure is the latent heat of fusion. So we already explained that we have the three phases or the three states of matter. Now to convert a solid into a liquid, and this first stage here is what referred to as the latent heat of fusion. This is our latent heat of fusion, or short form as latent heat of ice, specific latent heat of ice. Now, we also have a second phase here. To convert that liquid to gas, it takes us further to what we refer to as the specific latent heat of vaporization. Specific latent heat of vaporization. So to convert the energy required to convert a solid to a liquid at constant temperature and pressure is what's referred to as the latent heat of fusion. While the quantity of energy we would require to convert a liquid into a gas at constant temperature and pressure is what we refer to as the latent heat of vaporization, or short form latent heat of steam. So this brings us to specific latent heat of vaporization, the quantity of heat required to change a unit mass of a liquid to this gaseous state at constant temperature and pressure. Now, for our latent heat of ice, the experimental value for the latent heat of ice is 336 joule per gram. So this is 336 joule per gram. Now you want to express it in terms of joule per kilogram. So that will be 336. That will be joule per kilogram. So in terms of joule per gram, you have this. In terms of joule per kilogram, you also have this. Now the latent heat of steam, or the specific latent heat of vaporization, is expressed experimentally as this. So the range is between 2260 to 2268. Also, you can say the latent heat of fusion is 1/7 times the latent heat of steam. So in cases when we want to solve and we don't know the latent heat of steam, and we are given probably the latent heat of the ice, so our latent heat of steam will be equals to 7 multiplied by the latent heat of ice, by just changing of subject of formula here. So now we have a temperature time graph here. You have the temperature against time. Now you have various stages of conversion from the solid state to the liquid state to the gaseous state. So in the first instance here, we have a solid now, and this is solid ice at this initial stage. Now it has a temperature of minus theta degrees Celsius. It is cold, ice cold. So it has a temperature, a negative axis of degrees Celsius. So for us to convert our ice now to water, now we are going to apply a certain amount of energy, heat energy, which is Q. So the amount of energy you will be needing to convert ice to water, initially, you need mc theta. Remember the heat capacity to raise the temperature of that substance by 1 degree Kelvin is the heat capacity. Now the heat will be needing to raise the temperature of this ice in order to attain or achieve water is this mc multiplied by change in theta for ice to move to water now. So the additional energy required for us to convert ice to water, which is the latent heat, gives us ml. So recall that your latent heat is mass multiplied by the specific latent heat of the substance. So for us to convert ice to water now, the heat energy required to raise its temperature is given as mc theta. Now the heat required to change its state from solid to liquid is referred to as the latent heat. So this gives us mc change in theta plus ml. So similarly, moving forward, if you have water now, in this case, now this was solid and this is the liquid now. We've converted the solid to liquid. Now furthermore, to convert the liquid now to this gaseous state also. Now you have the liquid. To convert the liquid to gaseous, you require a certain amount of heat energy also. The heat energy required to raise the temperature of the substance per unit Kelvin, which is this heat capacity now. So to raise that mass of the liquid by a certain amount of temperature, that is the heat capacity, mc change in theta, then plus to convert a liquid to a gas now at this final stage, that is the latent heat also, but in this case now it is the latent heat of steam we are concerned about. So we've converted the liquid into its gaseous state. So this temperature time graph is a simple chart we'll be using when we are solving questions. So to convert a solid to a liquid, you need the heat capacity, the heat required to raise its temperature, plus the heat which it's used to transform from the solid state to the liquid state. Now, on getting to the liquid state also, the heat required to raise the temperature further to attain a gaseous state is the heat capacity here. Now, plus the heat required to change the state from liquid to gaseous, which is ml steam. So from these equations now, we can determine our specific latent heat of fusion, and we can determine our specific latent heat of vaporization, provided we are given the energy supplied or the energy required to convert the states of the substance here. Now, a simple experiment before we look at some examples now. Now we asked to find the latent heat of fusion of ice now. And you have a calorimeter and it has water. You have ice cube, and this is water, and this is the calorimeter. Okay, simple experiment to determine the latent heat of fusion of ice. Now you have a calorimeter of a certain mass, and the calorimeter has its specific heat capacity. The heat required to raise the temperature of the calorimeter, now let's say it's a copper calorimeter, it has its own specific heat capacity, and also it has its initial temperature, theta 1. Now the volume of water also in the calorimeter has its own mass, m2. Now water has a specific heat capacity of 4,200 joules per kilogram. It has its own specific heat capacity. Similarly, it has its initial temperature. Now lastly, for the ice which is being introduced into the system, the ice also has its mass. Ice has its specific heat capacity because ice is a form of water. to its specific heat capacity. Ice also add its initial temperature. But in this system now, what we are asked to find is the latent heat of ice. Now that amount of energy we use to convert ice into water. Now as this ice is introduced into the system, definitely it is going to melt, and ice will be converted from its solid state to a liquid state. So in this case, remembering the principle of calorimetry, the law of energy, that the heat gained is equals to heat loss. Now, remembering this when solving questions when you are dealing with heat energy now, because energy cannot be lost, it can only be converted from one form to another. Now, in this case now, we are dealing with heat gain and heat loss. Now, we need to identify where we gained heat and where we lost heat. Now, recall that water was at an initial temperature, calorimeter was at an initial temperature. Now, with the introduction of ice into the system, the water loses its heat energy. Now, let's say water was at a temperature of 30 degrees Celsius. Definitely, ice would be probably, let's say, 2 degrees Celsius minus 4 degrees Celsius, 0 degrees Celsius, minus 10 degrees Celsius. Basically, let's say less than 0 degrees Celsius. Now, introducing ice of minus 5 degrees Celsius into this system, and the ice gains its energy while water will lose its energy, because water will become colder while the ice will become warmer. So using this simple analysis now where are we going to lose it? Where are we going to gain it? Now the water will lose it because there will be a drop in its temperature from T2 to T3. There will be a drop in the temperature of the water. Now the calorimeter also will also lose heat because the calorimeter had an initial temperature θ1. On introduction of ice into it, it will also drop in its temperature to a new temperature, while ice would gain heat. The temperature would increase from minus 5 to a new temperature, probably 15 degrees Celsius, after the mixture has been cooled. And also there was the latent heat of fusion, the heat energy, the quantity of heat required to convert ice to water. So in this case now, the water lost heat, the calorimeter lost heat, while ice gained its energy to melt from ice to liquid. So in that case now, we have a system which is the gain equals to loss. Now since the ice gained heat, so we have mc theta, it gained an amount of heat now plus the energy, the latent heat, which it used to convert from ice to water, ml, now equals to the loss in its energy. The calorimeter lost its energy, mc theta. Now water also lost its energy, mc theta. So this simple idea is what we're using when we are solving. The same way we used when we are solving with respect to its capacities. But in solving its capacities, we are not concerned with the change of states. We are only concerned with increase in temperature of the substance. But in latent heat now, we are dealing with the change in states, of the substance. So quickly now we'll be looking at simple examples. So here I have a NECO past question. This is a NECO past question. 17, I solved question 17 in the previous topic on specific heat capacity. You can recall, we can check subsequent classes on the YouTube channel. So question 18 now is a question on latent heat. You can see now we have to calculate the quantity of heat required to melt 300 grams of ice at 0 degrees Celsius. The latent heat of fusion of ice is 3.36 times 10 raised to the power 5 joule per kilogram. So we are given the latent heat of fusion of ice already. So taking into account now, we should calculate the quantity of heat Q which will be needed to melt ice now from ice to water. So we are given ice at 0 degrees Celsius. Its latent heat as 3.36 times 10 raised to the power 5 joule per kilogram, and the mass of ice was 300 grams. So converting 300 grams to kilogram gives us 0.3 kilogram. Now you recall that the latent heat is equals to Q equals to ml. We have to find the quantity of heat required to melt ice. The quantity of heat required to melt ice, as the latent heat is equals to ml. So our latent heat would give us our mass, which is 0.3, multiplied by the latent heat of fusion. So this will give us 1.008 times 10 raised to the power 5 joule. So this is our answer here. So I have another example here. This is a WAEC past question, which I laid my hand on. So we have, we are told calculate the quantity of heat needed to change the temperature of 60 grams of ice at 0 degrees Celsius to 80 degrees Celsius. We're given specific latent heat of fusion of ice 3.36, specific heat capacity of water 4.2 multiplied by 10 raised to the power 3. So we have to interpret the parameters we're given here. Now we're told we should calculate the quantity of heat needed to change temperature of 60 grams of ice at 0 to 80. So automatically the ice had melted from 0 degree. It has melted into water already, and the temperature of the water is 80 degrees Celsius. So we're told to calculate the quantity of heat needed to change this temperature from 0 to 80. Now for we to have a change in temperature, we need its heat capacity, which is mc theta. Now also, because it had changed from one state to another state, we are also going to be interested in its latent heat. So that gives us Q equals to mc change in theta plus ml. So Q gives us, now we're told 60 grams of ice. 60 grams of ice. That's 60 grams converting to kilogram divided by 1000. So that gives us 0.06. Now we need the specific heat capacity of water we're given. That's 4200. The temperature change now, we are told from 80 degrees Celsius to 0 degrees Celsius. So 80 plus mass 0.06. Specific latent heat of fusion of ice is 3.36 times 10 raised to the power 5. Okay, so that gives us 0.06 multiplied by this, this gives us 2. This multiplied by this also gives us 2160. And adding these two together, we're going to have 40,300 joules, which is the same as 40.32 kilojoules. This is the quantity of heat required to change its temperature, and during that temperature change, there was a change in states. And for the previous example I solved, we asked to find the quantity of heat required to change its states. We are not concerned about the temperature change. It's changed states from ice to water. In this case, we asked quantity of heat needed to change the temperature of ice to from 0 to 80. Now at 80 degrees Celsius, that become a liquid already. Okay, so that gives us 40.32 kilojoules. So our answer is 40.32 kilojoules. Okay, so my reference material is Essential Physics. Okay, now I'll be picking questions from a lot of examples that are given here. So firstly, I'll be solving question 15. So as usual, we have to write out the parameters we're given. Okay, it says a heating coil of resistance 20 ohms. Now we have resistance of 20 ohms. It says it's connected to a 220 voltage source. Our voltage is 220 volts. And it says it is used to boil a certain quantity of water in a container of heat capacity 100 joules per Kelvin. And the heat capacity of the water which it is used to boil is 100 joules per kilogram. Now it is used to boil water for 2 minutes. So our time taken now is 2 minutes. So we are told if the initial temperature of the water is 40 degrees Celsius, calculate the mass of water in the container. So the initial temperature of water we are given is 40 degrees Celsius. Now you have to calculate the mass of water in the container. You have to find the mass of water. We are given its specific heat capacity. Specific heat capacity of water is 4.2 times 10 to the power 3 joule per kilogram. Now so we should assume the boiling point of water to be 100 degrees Celsius. So I've written out the parameters we're given. Now to interpret the question now, you have, and let's say we have used a kettle. Now you have a kettle which is connected to an electric kettle connected to a power source. Now the coil has a resistance of 20 ohms. The power source is 220 volts. It's used to boil water for 2 minutes. The electrical energy will be consumed from the power source, and the electrical energy consumed is being transformed into heat energy. Heat energy is used to boil the water. Now the heat capacity of the water is 100 joules per Kelvin per kilogram. Now the initial temperature of the water was this. We are told to boil water, so the boiling point of water is 100, given the specific heat capacity. Now what was the mass of water in the container? This is a WAEC past question 2002. So it's where the parameters were given: the resistance of the coil, voltage of the coil, the heat capacity, the time taken, the initial temperature, boiling temperature. We have to find the mass of water, and this was specific heat capacity of water. Now you add water in the kettle now. Okay, so we are told water was in the container which was used to boil, and its final temperature was 100 degrees Celsius, which is a boiling temperature. So means water converted to steam, but we are not given the mass of the steam which evaporated or which was retained in the container. Likewise, we are not given the latent heat of vaporization of the steam. So in this case, it might be that the water was yet to convert fully into steam. We are told to assume the boiling point to be 100. Assume the boiling point to be 100. So in this case now, the heat energy, which is Q, which was expended or which was used, will be equals to mc theta plus mc change in theta. Now this first one was for water, and this is for the container. Now we don't have plus ml. We don't have that because we are not specifically told if water converted into steam. So we are not concerned with the latent heat now. So the heat consumed by the whole setup is equals to the heat capacity of water plus the heat capacity of the container. It gives us the total heat energy. And also using the law of calorimetry or the law of mixtures, we have heat gained equals to heat lost. So where was the heat lost? We are told the heating coil. Now let's take it now as a kettle to a power source. Now, like I explained earlier, the power source it has the resistance, it has the voltage as our power source. Now energy is being converted from electrical energy to heat energy from the power source to this. Now this is the container. We are given the heat capacity of the container. The heat capacity of the container to be 100 joules per kilogram. 100 joules per kilogram. Now I'll employ us to follow the classes one after the other for us to have a good understanding. That's why I'm taking the classes one after the other. So from one topic to the other, we're progressing using what we learned from the last class. So from the last class, I told us, or 2 classes away, because the last class was on expansion, I told us Q is equal to MC change in theta. Now, C is equal to Q over M change in theta. Now, this is the specific heat capacity. This is specific heat capacity. While MC equals to Q by change in theta is the heat capacity. So they are literally different because specific heat capacity is the heat required to raise a certain mass 1 kg over 1 degree Kelvin. Heat capacity, heat required to change the whole mass now, the whole mass of the substance by 1 degree Kelvin. So we are told the heat capacity of the container, the heat capacity of the container was 100 joules per kilogram. That is settled. So this is the relationship we're going to be using. Heat is equal to this. Now the heat gained is equal to the heat lost. Now what gained heat, what lost heat? So you have heat energy from the source is being lost because you are using electrical energy. With time, energy is lost. You absorb energy from the power source, convert into its energy. So the electrical energy is being lost. The container gains heat energy. Water gains heat energy. So we'll be able to identify where energy was lost and where energy was gained. Very critical into solving questions. So that brings us to this now. The heat gained is equal to the heat lost. This is where we have heat gains. This is where we have heat lost. So for the heat gained now, that is MC change in theta for water. Water gained heat. Water is inside. Now the container also gained heat. Now equals to heat lost. Q, our heat lost is the electrical energy. So using this equation now, heat gained equals to heat lost. Our heat gained, that is mass of water, specific capacity of water, temperature change, plus mass of the container, specific heat capacity of the container, multiplied by temperature change, is equals to power multiplied by time, which is electrical energy, which is the electrical energy lost. Electrical energy is power multiplied by time. So the mass of water which we were given So which we are asked to find, we are not given. We are asked to find the mass of water, which is unknown here. So multiply the specific heat capacity of water is 4.2 times 10 raised to power 3. Now the temperature change, we are told our initial temperature was 40 degrees Celsius, final temperature was 100 degrees Celsius. So our temperature change will be 100 minus 40. Now plus mass of the container, specific heat capacity of the container, we don't know, but we are told the heat capacity of the container Q over change theta is given as MC. And we are told from the question that our heat capacity of the container is 100 joules per kilogram. 100 joules per kilogram. It gives us 100. So this is 100. Now multiply by its temperature change also will be 100 minus 40. Because the container is containing water. So if water was at 40 degrees Celsius, also the container would be at 40 degrees Celsius. So it equals to power multiplied by time. Now to find power, power is equals to IV multiplied by time. We are not giving voltage. We are giving voltage to be 220 volts, but we are not giving the current. So if you recall, that V equals to IR. So I is equals to V over R. So this becomes V over R multiplied by V gives us V squared over R. So this is our new power now. So the mass of water which we are asked to find multiplied by 4,200. 100 minus 40 gives us 60 plus 100 times 100 minus 40. 100 minus 40 is 60. 60 multiplied by this 6,000 equals to IV multiplied by T becomes V squared over R. Our V was 220 volts. Resistance was 20. Multiplied by time. Time was 2 minutes. Convert 2 minutes to seconds. So this gives us 4,200 multiplied by 60 gives us 252 mass of water plus 6,000. Now all this would give us 290,400. Okay, so it gives us MW will be equals to 290,400 minus 252 all over 6,000. It's going to give us 1.129 kilogram. So this is the mass of water in the container. Sorry, okay. So you have 290 minus 4. This comes outside minus 6,000 and divided by this. So it's still correct. Okay, I have another question for us to look at. They're told a 90 watts immersion heater is used to supply energy for 5 minutes. The energy supplied is used to completely melt 160 grams of a solid at its melting point. Calculate the specific latent heat of fusion of the solid. 90 watts, the power of the heater, used over 5 minutes. The energy supplied is used to completely melt this. So we lost the energy while the solid, as a result of melting, gained heat. So the heat energy lost is equal to the heat energy gained. Energy lost is equal to energy gained. So we have power multiplied by time to be equals to our latent heat. So that gives us the power of the heater we are given was 90 watts. And the time taken was 5 minutes. Converts to seconds gives us 300 seconds. Now the mass of the ice was 160 grams. To convert gives us 0.016 kilogram. We're told to find the latent heat. The latent heat of fusion of the solid. And we recall that Q is equal to ml. We're not concerned about any temperature change. The solid changed to liquid. That's the latent heat. And our latent heat is equal to ml. So you record that heat energy gained equals to heat energy lost, or energy gained is equals to energy lost. Now, the energy lost by the ether, that's power multiplied by time, equals to ml. So we lost this due to electrical energy. Electrical energy was lost from the immersion ether converted into heat energy. So the power was 90, the time was 300, our mass was 0.16, L, which is unknown. So this gives us 0.16. So it gives us 168,750 joule per kilogram. So for the immersion ether, the specific latent heat was 1,750 joule per kilogram.
I hope the class was interesting. If you have questions, please drop them in the comment section or send us an email. We will love to help you further. See you in the next class.